Okay, it's at 8:30. Let's go and get started. Good morning, everybody. How's everyone doing today? Good, doing good. Can everyone on Zoom hear me? We still have kind of a weird setup right now. Probably you'll notice my webcam is upside down because okay, good. Yeah, because I'm using the dock cam today. So I figured out that works, but it's the video feed is upside down. So yeah, it's kind of funny. Yeah, there I am, upside down. Okay. All right. So the plan for today is we're going to finish up our lecture notes on Fourier. We just have a little bit left, so probably about half a lecture's worth of content. And then we're going to move on then into the last kind of big unit for the class, which is probability and statistics. So this class, I think I've mentioned it before, but this class is kind of a weird kind of mishmash of lots of different math stuff. Basically, I know you guys have taken like the four class math series here. And they do a really good job. The math department does a great job here. But for engineering, there are kind of some more specific information that we want you guys to know. And this class is kind of like our chance to kind of catch up on all of those kind of somewhat random pieces of math. We kind of jumped around a lot already. And when we go to probability statistics, that's kind of another big jump that we need to do. For that. So today will be a little bit jarring, just as we talk about Fourier, we kind of reviewing, I think, just kind of basic probability and statistics. Okay, so some announcements. Just like I announced last week, midterm 2 has been pushed back. So originally the date for midterm 2 was going to be this Thursday, April 20th. But we are a little bit behind in the class, and so I originally planned to finish up Fourier last week. But because we're still finishing up this week, I pushed the midterm back a week. So the midterm is now going to be next Thursday, so April 27th. Okay. I've already posted the preparatory materials. So the study guide is online. And so if you go to the page for week 13, you should be able to download the study guide from there. I also posted a sample midterm. And so all it is just the midterm that I gave last time I taught this class, which was about 3.5 years ago. So, so the sample midterm is there for you to get an idea of kind of what to expect on the exam in terms of difficulty for the questions, and also just to give you more practical stuff. So I just posted the questions for now. I'll probably post the solutions for that practice midterm probably on probably over the weekend, on Sunday or so that you have solutions there. Okay. And just like the first midterm, I plan on recording a review video. So this is going to be outside the class, just because of we're going to catch up and cover everything that we need to. So the review video, I plan on recording it and posting it on Friday. So you'll have it for the weekend. If you want to study over the weekend, and it'll be there, well before the midterm on next Thursday. Okay. Another announcement. I forgot to put it here, but homework work 6. The Fourier transform homework. I was a little bit late in posting that. I know originally I said I would post it last Friday, but I kind of got sick a little bit over the weekend, and so I wasn't able to post it until yesterday. So I pushed back the due date for that slightly, just to give you guys a bit more time. So homework 6 is now due on Sunday. Okay. So as you can tell, I'm still a little bit under the weather, so I might be a little bit low energy today, but I'll do my best. Last week I was hungover. This week I'm sick. Hopefully next week I get overall. Maybe I'm sick because I was hungover. Okay, so I think that's all my announcements. For the second midterm, the things that you can bring are still the same as the first midterm. So you can bring a calculator, you can bring a writing utensil, and a cheat sheet. So double-sided, 8.5 by 11 sheet of notes. I'll send all that information in an announcement today, just to kind of show you where the study guide is, where the practice midterm is, and kind of just reiterating kind of what you can bring to the second midterm. All right. So I think that's all my announcements. Are there any questions I can answer before we get started for today? Okay. All right. So let's go and get started. And so where we left off last week was this idea of the Fourier transform. And so the Fourier transform is one of the two kind of transformation techniques that we're learning in this class. And so the idea is to take a function in the physical domain, okay, and specifically the time domain, and transform it into the frequency. Because Fourier, whenever you see Fourier kind of in practice, it's all about frequency. Okay. And so traditionally, when you think about frequency, you think about periodic functions, the functions that can actually repeat. But you can actually apply the Fourier transform to even non-repeating functions. And so that's the whole idea. And so when we're covering Fourier series is mostly limited to those kind of periodic or repeating functions. Fourier transform is more broad. You can apply it to almost anything. Okay? And so the idea with Fourier, and kind of the main reason why people perform it, is that by kind of changing this variable and by looking at it from a different domain, you learn a lot more different information about the function that you wouldn't have. Well, it's a lot easier to see certain types of information in the Fourier domain versus the time domain. Okay. And we'll go over that a bit more later today when we talk about the power spectrum, the Parsifal thing. But first, the first thing I want to go over today is kind of a different form of the Fourier transform. So, so far, when we talk about Fourier transform, it means that we're computing two different functions. And that is the sine and cosine Fourier transform. Just to kind of remind you, when we talk about the cosine Fourier transform, we mean the function a of omega, okay? And the sine Fourier transform is the b of omega function, okay? Mostly just because these transforms are paired together with the sine and cosine. So this is nice, especially if you have a function which is either even or odd, right? And so for even or odd functions, then these kind of simplify very well, okay? But it's still kind of annoying to have to compute two different functions to get the full Fourier transform. And so the first thing we're going to cover today is kind of a more, I would say, more complete form of the Fourier transform. We just compute one instead of two functions. And so the first question we're going to answer, is there a way to combine these into a single transform? And of course, the answer is yes. Otherwise, I wouldn't ask this question, right? And so what we're going to make use of here is our famous Euler's formula, Euler's relation. And so Euler's relation said that if you have a complex exponential, so e to the I times some function, and so I'm just going to say it's just x for now. Okay. This is equal to cosine of that variable plus I sine. And so we can use this to basically combine together the sine and cosine transformed into just one expression. Okay. We're going to use this to combine together our expressions for a of omega and b of omega into one kind of expression. So that expression we'll call f of omega. And usually we give it a little hat is equal to 1 square root of 2 pi integral from negative infinity to infinity of your function f of t. Where f of t is your time domain function that you want to transform, times e to the minus I omega t and so this right here, this formula is what is known as the complex Fourier transform. So this is a general transform here that can work for both, even and odd functions, but it can also work for functions that are neither even nor odd. Okay. And the corresponding inverse. And so remember, for Fourier transform, we have formulas for the inverse as well. And so remember, the inverse takes our Fourier transform function, f of omega, and transforms it back into the time domain. So we have 1 over square root 2 pi, and then go from minus infinity to infinity. F of omega e to the I omega t d. And so when you have a function that's neither even nor odd, this is going to be your best option because it kind of saves you some work. On the one hand, usually integrating with an exponential like this is a little bit easier than integrating with a trig function. And so there's that benefit. Not always, but most of the time. And also it saves you from having to compute 2 expressions. So this lets you just compute just one. Okay. All right, any questions on this before we do an example? Okay, so let's do an example to see how this is done in practice. Okay. All right, so for this example, let's find the complex Fourier transform . Let's find the complex Fourier transform of the following function. We have f of t is equal to, and f of t is going to be equal to 2 different zones here. And so we have 0 when t is less than 0. And when t is greater than 0, f of t is going to take the form e to the minus alpha t. And so visually it looks something like this. And so from t is from minus infinity to 0, or f of t is going to be just 0, just like this. Okay. Then when t is greater than or equal to 0, we're going to jump up. We have a value of 1 here. Decaying exponential just like that. Okay. And so what we want to do is we want to find the complex Fourier transform of this function. So all we have to do is plug in. Okay. So f of omega function here. The complex Fourier transform is 1 over square root of 2 pi. We go from minus infinity to infinity. F of t e to the minus I omega t dt. Okay. We're going to plug in for ft here. And since we have a discontinuous function, remember we can always break up our integral into 2 different domains. And so we're going to have one domain from minus infinity to 0, and then another domain from 0 to okay. And so we break this up. We have f of omega, break it to half, equal to 1 over square root of 2 pi. There's integral from minus infinity to 0, 0 times e to the t t plus integral from 0 to infinity e to the minus alpha t e to the minus I omega t So of course, the first integral is just going to be 0. So we're just going to cancel this one out. And so our second integral, what we have is f hat of omega equal to 1 over square root of 2 pi. Integral from 0 to infinity e minus alpha plus I omega t dt. And so I had two exponentials multiplied by each other, and so they have the same kind of root, or the e is the same on both, and so we can just add their exponents together just like that. Okay. Okay, so from here it's a pretty simple task. We're just going to integrate this exponential function to 1 over square root of 2 pi. Integrate this, we get minus 1 divided by alpha plus I omega minus alpha plus I omega t evaluated from 0 to infinity. Okay. So if we evaluate those integration bounds, remember we're plugging in for t, okay? That's our integration variable. If we do that, we get 1 over square root 2 pi minus 1 over alpha plus I omega. Okay. We're going to have e to the minus infinity times alpha I plus I omega, so that's e to the minus infinity. Minus e to the minus alpha plus I omega 0. Okay. E to the minus infinity is just going to give us 0, and then e to the 0 is just going to give us 1. And then this negative here is going to cancel out with this negative. Okay. So if we pull it all together, we have f of omega is equal to 1 over square root of 2 pi by the quantity alpha plus I. And that right there is our solution. All right, any questions on this example here? Right. So again, the complex Fourier transform, it works great for situations where you have basically neither even nor odd. Okay. For the homework 6 and for the exam 2, I'll probably tell you, whether I want the complex Fourier transform or the Fourier integral. But just know that in general, if you have a non-even, non-odd function, the complex Fourier transform works. Okay. All right, so that's about it. And so that's it for the calculation portion of Fourier transform. There's really not that much to it. But I do want to talk about some more conceptual things that have to do with Fourier. Okay. Things like kind of the engineering applications, and one very important kind of theory have to do with Fourier as well. Okay. And so first thing we're going to talk about is we're going to revisit this idea of the power spectrum. The power spectrum is probably the most important application for Fourier, at least from an engineering point of view. Okay. And so even if you forget all the details of, computing Fourier series, computing Fourier transforms, as long as you understand kind of conceptually what the power spectrum represents, I would consider that a victory for this section. But still try to remember all the other stuff. Power spectrum is probably the most important thing. Okay, so what is the power spectrum? So we talked about this before in Fourier series, but it's worth kind of repeating here, right? So the power spectrum is basically something you can get out of the Fourier series or Fourier transform that represents how strong certain frequencies are in a random function or a random signal. Right? So I think I kind of left it at that, when we talked about Fourier power spectrum before, but the word strong here is kind of key to this whole understanding, right? So when I talk about how strong a function is, what I mean by that is, what is the amplitude of the signal for that given frequency. Right. So remember, Fourier always kind of comes back to this idea of frequency and amplitude. Frequency and amplitude. When we first started talking about Fourier, we talked about the concept of sound, right? And so that kind of persists here as well. So let me give you kind of a visual example with two frequencies, just so that you can kind of see. Right. So let's say that we have a function here, and there are two basically dominant frequencies in this signal. Right? And so on the one hand, we have kind of a lower frequency signal, and so we have a slow oscillation. So maybe the function kind of looks something like that. Right? But on top of this, maybe we have some high frequency noise. And so, maybe your measurement device is not very stable, or it's not very, not very nice. And so on top of this, you may have some kind of high frequency signal. And so you have a signal that kind of looks like this. And so, if you look at kind of the longer term pattern, you can see that there's kind of a slow oscillation here. But on top of that slow oscillation, you have kind of this high frequency noise that's kind of superimposed on top. Okay. And so we have high frequency noise. And so, one thing we may be interested in is, what is the relative strength or what is the amplitude of the low frequency signal relative to the high frequency noise? Okay. And so something you may be interested in computing is, what is the signal to noise ratio? That's something that's usually computed for things like this. Okay. And so what you can do, use a different color for this. And so for the low frequency signal, right, we can compute the amplitude of that signal, right? Right. So that's kind of approximate. And so, the approximate amplitude of the low frequency signal is given by that. Okay. And for the high frequency signal, it's a lot less. And so, it's a little bit harder to draw kind of this measurement from this peak here. This right here would be the frequency of the high, or excuse me, the amplitude of the high frequency signal. So for this simple case, this is something that we can kind of easily kind of visually see and kind of visually draw. But kind of the mathematical tool that kind of gives you this information is Fourier. Right? And so if we were to take the Fourier transform of this, or the Fourier series, okay, what this is going to allow us to do is that it's going to allow us to form the power spectrum of this signal. And so for this signal, it would look something like this. The power spectrum, always on the horizontal axis, we're going to have frequency. And on the vertical axis, we're going to have amplitude. So here we have two dominant frequencies. So here we have a low frequency. We also have a high frequency. And so the height of the power spectrum for each of those frequencies tells you basically what the amplitude for that frequency is. Okay. So for this particular example, for that low frequency, we have a relatively high amplitude. Okay. And for the high frequency, we have a lower amplitude. Okay. And so for this particular case, we have a high, signal to noise ratio. So we can even with the noise there, we can still basically pick out what the signal actually looks like. All right, any questions on this? Okay. All right, so Fourier basically gives us a way to compute this this power spectrum. Okay, and it has a lot of other applications as well. So if you've ever if you play a musical instrument, I think guitar is kind of the easiest one to kind of visualize this with, right? If you pluck a guitar string, right, it plays a certain sound, right? And so it plays a sound at a certain frequency. And so you can basically do a power spectrum analysis of the sound that comes off a guitar string, and you'll see that the main dominant sound is whatever the guitar string is is tuned to. Okay, but another application that's particularly relevant for mechanical engineering is vibration testing or frequency response testing. Okay. So every structure, every object, I would say, every object in the world has a resonant frequency. Okay. And if you recall, from we discussed about frequency kind of very early in class, that if you force an object at its resonant frequency, that it's basically going to break. Okay. It will usually break in a very spectacular way, and so it'll be fun to look at, but it would not be fun to pay for it or to fix it, right? And so whenever you're designing a structure, especially kind of a larger structure like buildings or bridges, engineers always have to be aware of what the resonant frequency or what the natural frequency of that structure is. Okay. And so how does one find the resonant frequency? So how do we know what that is? Well, one way to do it is to do a frequency response test. And so what's typically done is that if you have some kind of structure, and you apply some kind of impulsive loading to it, so basically you just apply, like you just kick it basically, right? So you apply some kind of forcing that occurred very quickly. From there, you observe the vibrations that result. Okay. Let me give you an example. So let's say that we have a potato-like structure, but I guess this looks like a pear. So this is our mechanical structure. And so what we can do is we can apply some kind of forcing to this structure. So let's say that we just kick it or something. Right. After you kick the structure, or after you apply your impulsive forcing, the structure is going to start to vibrate. And if you are kind of smart about it, you can attach a device to the structure to measure these vibrations. So usually it's going to look something like this. It's going to look like this. So how do we go from something like this, so a very messy time domain signal, and how do we pick out what the resonant frequency is? Well, a good tool that we can use here is Fourier. And so what Fourier is going to do is that it's going to transform the signal, this messy signal, it's going to transform it into the frequency domain. And what you're going to see is that the signal is going to look something like this. There, okay. Where these two peaks are the resonant frequencies. These are the natural frequencies of the structure. Right. So the engineer has to be aware of these. And so, they want to make it so that the natural frequencies are not something that, can easily be achieved. Right? And so this is particularly relevant to California, because in California, we have earthquakes that happen on a semi-regular basis. Right? And so if you're designing a building in California, you want to make sure that the design of the building is such that, the natural frequencies of the building don't match up with an earthquake frequency. Otherwise, your building will shatter and you'll probably lose your job and lose your career, which is usually not good. Okay. Any questions on this? Okay. All right, and so another application for the power spectrum is in signal filtering. And so in the world of signal processing, so this is a little bit more on the electrical engineering side, but in the world of signal processing, a lot of times you get signals that have a lot of noise associated with them. A lot of times, we're not interested in the noise. We're interested in kind of the signal underneath. Right? And so oftentimes we want to filter out the noise from these signals. And so let me bring back the example from earlier. So let's say that we have a low frequency signal with a high frequency noise on top. So let's say we have something that's like this. Right? So clearly here, we have some kind of low frequency signal. Those are the two kind of big humps that you see. But on top of it, we have this high frequency noise that we're not really interested in. Okay. And so what we could do to filter the signal is we can run this through something called a low pass filter. And so what a low pass filter means is basically we're going to only let the lower frequencies pass through, this filter. Right? And so the way it works is we're going to take the Fourier of this signal, Fourier transform. And it's probably going to look something like this. So frequency here, omega, f of omega. And so we're going to have a big spike, a lower frequency, and so that has to do with the signal that's already there. And for the higher frequencies, we may have something like this. So, basically everything after this point right here, everything past over here is just the noise. So it's not really anything useful for that. Yeah. And so what we could do, one kind of very basic form of a low pass filter is just to truncate the Fourier transform at that cutoff. Okay. You could truncate the Fourier transform and then reconstruct the signal without those higher frequencies. Okay. And so the result, in the best case, would look something like this. So if we're truncating all those higher frequencies, then those higher frequencies are not going to show up in our filter signal. And so we would have something that looks like this. And so our signal now is a lot smoother because without all that high frequency. Okay. So that's kind of another application of the power spectrum. So there's even more applications in this. So I could go on for the entire lecture for more applications. But I would say these are kind of the most relevant ones for engineering. So we covered kind of mechanical engineering, a little bit of civil engineering, and electrical engineering here. Okay. All right, any questions on this so far? Okay. All right. So the last piece of theory that we're going to cover with regards to Fourier is this idea of Parsifal's theorem. Okay. And so the idea of Parsifal's theorem kind of leads directly off this idea of truncation. So truncation is something that you're going to do a lot in Fourier because most of the time you don't really need those really high frequency terms either in the Fourier series or in the Fourier transform. But then that kind of begs the question of if we truncate if we truncate our Fourier expressions at some cutoff, how does that change the nature of our function? How does that change the nature of our signal? Okay. Because obviously, it has kind of a smoothing effect. We just saw that with the low pass filter. But what other effect does that have on our function for the signal? Okay. And so what Parsifal's theorem states is that, another way that you can view the power spectrum is that the power spectrum kind of tells you how the energy in your function is distributed among the different frequencies. hence the name power spectrum. So power spectrum is directly associated with just how much energy is being distributed. Okay. Right. So think of our frequency response test, right? And so if you take a structure and you literally kick it, right? When you kick a structure, you're kind of introducing energy into that system, right? So the kinetic energy of your foot when it strikes the structure gets transferred into that structure, and as the structure kind of dissipates that energy, it'll vibrate. Okay, that's kind of essentially what's happening from an energy point of view. Okay? And so the power spectrum basically tells you that, if you have kind of excess kinetic energy or excess energy in your system in general, the power spectrum tells you how that energy is distributed among the frequencies. Okay? And so if we truncate a signal, okay, if we cut off certain frequencies, effectively one thing that we're doing is we are reducing the amount of energy in the signal. And so that's kind of one thing to keep in mind when you're truncating. So when you're truncating a function, or truncating its Fourier expressions, it's just naturally going to have less energy than it did before. Stated another way, so another way to state this is kind of the more traditional kind of statement of Parseval's theorem. Okay. A complete Fourier representation the function must include all the associated frequencies and terms associated with that Fourier representation, all the way up until infinity. We can kind of state this elegantly into a kind of a formula expression as well. Right, and so if we take the integral of some function of t, take its magnitude squared dt. Okay. This here represents the power or the energy in that signal. Okay. According to Parseval's theorem, this is equal to the full Fourier transform expression squared. So integral from minus infinity to infinity. F omega squared. Right here is the minus. Right, so that's kind of the formula form, or kind of the mathematical form of Parseval's theorem. All right, any questions on this? Okay, all right, so that does it for Fourier. Okay, and so for the last 20 minutes of class today, let's go ahead and move on to the next big topic. So this is the cutoff right here. So midterm 2 content stops right here. Okay, so what we're going to cover from here on out, it'll be on the final exam, but not on midterm 2. Okay. And so for the last kind of big unit of the course, we're covering kind of this broader area of probability and statistics. So it's like I mentioned earlier today, it's a big jump, right? And so, this class is it's a bit difficult. It's a bit difficult to teach, but I imagine it's a lot more difficult to take just because we're jumping around between topics so much. Right? But the reason we cover probability and statistics is that having a good grasp, or at least a good grasp of the basics of probability and statistics, is really important for all the lab classes that you're going to take in the future, and probably you've already used if you've taken 368, 360. And so we'll be kind of giving like a good tour of probability and statistics. So I think today will probably be probably a review of some things that you already know. Probably Thursday we'll continue to review things you already know. So very simple concepts like mean, median, and mode. Data representation, things like that. Okay. And then we'll get into some more advanced topics like things like confidence intervals, things like scatter plots, regression, and okay. And so let's kind of introduce this first. And so let me start by saying that usually when you think about math and you think about kind of the performing a mathematical technique, you do it in a deterministic way. Okay. And so what I mean by deterministic is basically if you have a formula, if you have an equation, there is one answer to that equation. And so basically there is kind of a direct correlation. So one question has one solution. Right. I give you a differential equation. There is one solution to that differential equation. I give you a certain time domain function. There is one Fourier transform associated with that. Okay. Deterministic. Unfortunately, the real world isn't quite this simple. So there's not just one answer to every question or every problem there is out there. Because something that happens in the real world that we often don't account for in our mathematical calculations is this idea of uncertainty, right? And so the idea with uncertainty is that, you don't really know, what the answer is to every single problem or every single question, because there are kind of somewhat, at least perceived as random factors that affect the results. And so this uncertainty makes it very difficult to give like hard predictions in terms of what's going to happen in the world. If uncertainty didn't exist, then life wouldn't really be exciting to live, because then we would know everything that would happen. Probably we'd be ruled by the AI. We are already. But let me give you a very simple example. And so let me ask you a very simple question of, how long does it take you to commute to school? Okay. You can ask anybody this question. So you can go out into the quad right now and just ask this random people, and I guarantee you everyone is going to give you a similar type of response. I mean, everyone's response is going to be different, but everyone's going to give you this type of response. And so you'll probably hear people say approximately something. No one can tell you with certainty that every day when they commute to school is going to take them, 25 minutes and 42 seconds, right? That's impossible. It's impossible to predict down to the second, how long it takes you to come to school. And why is that? Why is it impossible to predict down to the second? Well, there's a lot of uncertainty that affects your commute to campus every day, right? Okay. And so let's list out, some factors that can affect your commute. So some things like traffic. Right? That's always the big one. 2 is parking. Especially on this campus, parking is a nightmare sometimes. Right? And maybe you had to stop for gas. Maybe there's construction. Maybe there's things like weather, pedestrians, cat right across the road, dog right across the road, rain, there's lots of different things. And so, there's, because of all this uncertainty, when you get your car to drive to campus every day, or even if you live on campus, even if you walk to class here, there are still unknown factors that, when you put on your shoes and leave your door, that are impossible to predict, just because we don't really have omnipresent. Okay. And so because of all this uncertainty, it affects your answer. Right? And engineering, it really isn't that much different. And so when you're constructing a building, or when you're designing a part for a mechanical machine, right? There are still going to be unknown factors that are going to affect your design, right? You may design your part kind of perfectly to fit one situation, right? But the reality is, whenever you design something, it's going to be exposed to lots of different types of situations. Okay? And so when we have results here that can be affected by uncertainty, we need to kind of take a different way of looking at these problems so that we can affect for all this variance. And so the term that we use for this mathematically is we use the term random data or random variable. And I don't use random, and so I think when people normally say random, they really mean like kind of true random, true chaos, or it's just kind of just does whatever. Okay? So I don't mean random in that sense. I don't mean random where things can just be literally whatever they want. Okay. I use the word random here just by the fact that it can change. Whenever we ask a question like this, the answer can change, depending on the situation. But it always kind of changes within a certain bound, right? And so it changes, but it changes within certain parameters. Okay. Okay. And so what we're going to go over today is kind of how to represent this data graphically. So today's all about kind of what I call data representation. All right, any questions on this so far? Okay. All right, so let's talk about some other important applications in engineering regarding probability and statistics. But where are you going to see this the most? All right, so the first place we're going to see it the most, if you haven't already seen it, is in lab measurements. Right, so whenever you do any kind of laboratory experiments or you take any kind of measurements, you know that there's some kind of uncertainty associated with that. Even for the most meticulously set up experiment, whether it's the devices that you're using to measure, there's some uncertainty associated with that. Okay. There's some uncertainty in the process, usually the physical process of which you're measuring or you're experimenting with. Okay. And so there's always going to be some uncertainty, and so you always need to take a probabilistic viewpoint whenever you look at lab testing. Okay. Okay. Number two is a fairly broad statement, but if you're ever in, when you start to work on design, right, you have to kind of predict for some kind of unknown things that are going to happen. And so the most common way that this is applied in practice is you probably have heard the term factor of safety, right? And so when you're designing a structure, you have to design it with a factor of safety in mind so that it can be, it can withstand any kind of, unknown kind of spikes in the loading or any kind of unknown effects that may occur. Okay. And one particular topic that is very hot right now is machine learning or artificial intelligence, AI. Okay. And so just the way that AI is designed, just from the ground up, from its core, it takes a lot of this uncertainty into account, right? And so if you look at like the source code for like ChatGPT or something like that, right? There's going to be a lot of probabilistic models. There's a lot of random variables that are assigned there, because every situation is kind of different. And so the AI, the way it's being trained, the AI is being trained to kind of have this uncertainty in mind as it's kind of giving you answers to, as you're telling ChatGPT to write your essays for you, right? And so there's, and that's kind of how it kind of varies its responses to different questions. Okay. Yeah, and so if you kind of read the theory in machine learning and AI, there's kind of uncertainty kind of baked directly into it. Okay. Okay. All right, and so let's start with the, so those are the applications. And so let's start with kind of the idea of representing data. Their data representation. Okay. And so whenever you have a collection of data, it could be for the exact same phenomenon. The first thing that you should be thinking about is, how do we represent this data in a way that we can easily interpret. And so the first way, or the first thing that people use to just record data is to put it in kind of a tabular or ordered list type of format. For example, let's say that, for the entire semester, let's say that you recorded every day, how long it takes you to get to school. Let's say you recorded, for every day of the week. You did it for, every week of the semester. So week 1, 2, 3, so on and so forth. And so the table format is very simple. You just basically record all the entries in the table. Wow, I wrote these notes a long time ago. So this is when it took me about 15 minutes to get to campus and stuff. I'm getting a lot farther away now. Let's say on Monday, maybe it takes you 13.93 minutes. Tuesday, let's say it takes you 16.41. Wednesday, 15.01. Thursday, 14.74. Friday, maybe Friday's really fast, so it takes you 11.1 minutes. Okay. All right, so this is usually the first thing that people do because this kind of format. So this is I call it like the Microsoft Excel or the Google Sheets kind of format. It's very easy to record information in this format. And so this is usually kind of your first stop shop in terms of, you have some kind of random event or random occurrence, usually you're going to record the table before. Right. So the table format is nice just because it allows you to record data, but it's a little bit difficult to kind of see the trends in the data or to see kind of its random variance or even its average. Okay. And so what we'll talk about on Thursday is, what are some graphical ways that we can represent data, right? Maybe you probably used some of those tools already in your lab classes, and then how that's more useful than this table format. All right, any final questions before we wrap it up for today? All right, so that's all we have time for today. So thank you guys for coming out today. And so remember all the midterm preparatory stuff is posted online, so make sure you take a look at that as you're studying. Homework 6 is due this Sunday, so make sure you get a start on that. And let me know if you have any questions. But yeah, besides that, hope you guys have a good rest of your day, and I will see you on Thursday. Yeah. Yes, usually that is the finite element month. Wait a second. No, we use ANSYS. ANSYS is finite element software, so it's basically you take, because SolidWorks you design a part of SolidWorks, and so in ANSYS what you do that you take that part and you kind of simulate what it would be like if you expose that part to loads or constraints. And so you can simulate things like what the stress is going to be in that structure, what the deformation is. Well, very biased, of course. I think the course, and so I don't think it's that hard. So there's one midterm in the course. There's no final exam, and so the main deliverables are going to be a midterm project where you use ANSYS to analyze a part, and a final project where you kind of do a little bit more complex finite element analysis, and one midterm exam based on the conceptual stuff.
So those projects are group collaborating groups?
No, they're individual projects.
Is it mandatory? I saw
No.
Mine was pretty good.
No, it's not. So it's basically the same style that I have here. So
Like preparing for midterms and quizzes and whatnot.
exactly.
Maybe because
Yeah.